SPH4U fields. 4.1 Gravitational fields. So gravitational fields exist in the space surrounding an object in which the force of gravity exists. So there is Newton's law of universal gravitation, which is Fg is equal to big G times m1 m2 over r squared. So in order to understand what these variables mean, I'll draw a diagram. So you have mass 1 here and mass 2. So m1 and m2, they just signify the masses of these respected bodies. And r squared, so r is actually the distance between the centers of each body. So that's really important. So, and g, that is a constant. So g is equal to 6.67 times 10 to the negative 11 Newton times meter squared over kilogram squared. So that is Newton's law of universal gravitation. And when you're close to the surface of a planet, so such as Earth, Fg, F small g, is equal to Fg. So F small g is what we remember from dynamics. That's equal to mg. F big G, that is Newton's law of universal gravitation. So we get mg is equal to g m1 m2 over r squared. Let's just say this is m1. m1, they get canceled out, so g is equal to g m over r squared, where little g is equal to the gravitational field strength. So now we're going to tackle a question that deals with gravitational fields. So determine the magnitude of the force of gravity when two uniform balls of mass 4 kilograms are separated 45 centimeters away from their centers. So we have Fg is equal to g times m1 m2 over r squared. So that is equal to 6.67 times 10 to the negative 11 times 4, or we could just say 4 squared, over 0.45 squared. So that comes out to be 5.27 times 10 to the negative 9 newtons. Satellites are objects or bodies that revolve around another body, and space stations are just artificial satellites that support a human crew and remain in orbit for an extended period of time. So think the International Space Station. And for the test of this course, satellites make circular paths, so we can state that Fg, or the force of gravity, is equal to Fc, centripetal force. So with this relation, we can state this. So g m of s, so that's the satellite, times m of e, that's the mass of the Earth, over r squared, is equal to m of the satellite times velocity squared over r. So if we do some rearranging via algebra, we can find that the velocity of a satellite is equal to square root of big G times the mass of the Earth, or whatever it is revolving around, times r, or the distance between their centers. And with this relations Fg is equal to Fc, we can also get this. G m1 times m2 over r squared is equal to 4 pi squared over m2r over t2. So this might be used in a question as well. And remember, for the r, that's from the centers between both bodies. So if you're given the distance from the surfaces of the satellite and the planet that is revolving around, then you need to take into account the distance that is from the surface to the center of the planet and from the surface of the satellite to the center of the satellite, because that's very important for the math here. So here's an example of a satellite question. So the Hubble Space Telescope, or in this case HST, is in a circular orbit and is 598 kilometers away from the surface of the Earth. So what is the velocity of the Hubble Space Telescope? So first let's find r. So r is equal to 598. Let's times it by 1,000 so we get everything in kilometers, plus 6.38 times 10 to the 6. 6.38 times 10 to the 6 is the radius of the Earth, and we need that because that would find the distance to the center of the Earth. So that comes out to be 6.98 times 10 to the 6 meters. So in order to find the velocity, we use the equation v is equal to g me, so mass of the Earth, over r. So that's equal to 6.67 times 10 to the negative 11 times 5.98 times 10 to the power of 24. And then all this is over 6.98 times 10 to the power of 6. So velocity comes out to be, and this comes out to be 7.56 times 10 to the power of 3 meters per second. So now we just need to convert this into kilometers per hour. So in order to do that, we would have to divide this by 1,000 and then times it by 3,600. So this divided by 1,000, then multiplied by 3,600. Okay, and then that comes out to be, the velocity is 2.7 times 10 to the 4 kilometers per hour. So in order to find the orbital period, we can just use the equation v is equal to d over t. So velocity is equal to distance over time. In order to find the distance, it's just 2 pi r. So that'll be equal to 2 pi times 6.98 times 10 to the 3. So that's equal to 4.3 times 10 to the 4. So we can rearrange the v is equal to d over t to be equal to t is equal to d over v. So period is equal to 4.3 times 10 to the 4 over 2.72 times 10 to the 4. So that comes out to be 1.6 hours. So the orbital period of the HST is 1.6 hours.